Okay, so we've talked about wood structures, we've talked about fabric covering, we've talked about sheet metal. Now we're going to talk about, instead of the old school way of doing things, we're going to talk about the new school way of doing things, and that is composites, particularly advanced composites like carbon fiber. Now, it is fundamentally different than pretty much anything that we've looked at before. It's very different than sheet metal in a lot of ways. It has some similarity with like laminate wood structures because you laminate the composites, and you'll see some similarities there. But composites on just kind of on the whole are like a whole new space age type technology. And so we're going to explore that. We're going to first look at the history of composites and like where did they come from, how did they come about, and then we're going to say like, hey, this is its employment in aviation, and now this is where things are going, because the future aircraft are going to be all composite aircraft. There's just like no other way, going about it. They don't corrode. They don't, as long as they're painted, they generally are blocked from UV rays. So they can sit on a flight line and be just fine. They are, a fraction of the weight, and they are 10 times as strong whenever they're built correctly. And you don't generally see a lot of problems with it. Now, there's been some aircraft that have come out that have had design flaws that were found out as the aircraft were employed and used at scale. But for the most part, the composite world is really revolutionizing how future aircraft are going to be built. And so this is a good thing to get your head wrapped around, to understand where aviation is going, and to be super useful wherever you end up going. There's two real kind of like worlds where aviation is just being revolutionized over and over again. One is with avionics, and that's just kind of ongoing, but you'll eventually hit a point of diminishing returns where you just can't digitize everything to the nth degree, or automate everything to the nth degree. You still have to have some level of human interaction there. But the other one is in composites, and composites are a lot slower because it takes construction, and then like you have to wait for the present inventory that's being used to just slowly attrit, so that way it can be replaced with new inventory that's coming out. So you'll start to see composites probably in the next 10 years or so will be as big of a deal as like the avionics kind of revolution has been for the past decade or so. So this is something really good to pay attention to. Now, we're going to start off by just simply talking about like what is composites. So we'll go through the history of it. And we're going to say like, okay, like what is it? What are the like the fibers? What's the core material? What's the resin? Then we're going to talk about storing those types of materials, and then we'll go on to eventually get to where we can repair those types of materials. And in class, this is what you're going to do. We're going to have you design a composite structure. Then you're going to build somebody else's design that they built, and then you're going to end up repairing a composite structure that was designed and built by somebody else. And so that should give you a pretty robust understanding of how composites operate, and like how what they're all about, and how to inspect them, and how to repair them, and all that good stuff like that. So, welcome to composites. All right, so composites actually can trace its roots back to the Treaty of Versailles. Now, what the Treaty of Versailles did after World War I was limit the ability of the German people to develop a mechanized army, or an army of any sort. And so a lot of their officer corps would train with like broomsticks and handles, and they knew that aviation was going to be really big, but one of the things that the treaty limited them on was putting motors into aircraft, because then they thought like, well, if they don't have motors, then they can't build an air force. Well, they actually were wrong about that, because what that forced the German army to do was, or the Luftwaffe, the German Air Force, to do was use gliders. Well, gliders is all about power management, and power management, come to find out, is critical in dogfighting. So what they inadvertently did was make one of the deadliest aerial fighting forces the world's ever seen by taking away their motors. Well, so these Germans grew up, as youngsters in Hitler Youth gliding clubs, and then they later on went to serve in the Luftwaffe, and continued to glide and sail and do that and fly. And even to this day, there's a very vibrant gliding community in Germany. Now for other reasons, but it's kind of part of their culture and heritage. Well, this goes on to, you at the post-World War years, and Germany's starting to rebuild, and all of a sudden people are like, hey, we're not Air Force pilots anymore, but we still like to fly, and we still want to glide. Let's start trying to build better gliders. So in 1958, the Phoenix took flight. Now, up to this point, all the gliders had been made out of wood, just like any other kind of classic airplane. They were just optimized to be super, super lightweight. But of course, like as we've learned, wood and cotton don't really bode well for airplanes for a variety of reasons. And so they were always looking for what's the next best structure or the next best material we could use to make the airplane lighter, to make it stronger, to make it be able to weather the elements better. And if we can make it stronger, we can make the wings better, that we can glide farther, longer, and get more bang for our buck. And so the glider. In 1958, you get the Phoenix. The glider became an all-composite structure, and this kind of marked the end of what they call as the classic sailplane area. That there's no more wood structure, planes being built. There's no more, fabric over the wings. Now it's going to be all fiberglass, and to this day, almost all your gliders, at least all the ones that I know of, they're all composite and they're all super lightweight for this reason. But that was the first ever airplane that was made out of all composites. But the story doesn't end there. I mean, obviously there's no motor, so its availability or its usability is extremely limited. And so somebody needed to come along and try to up the ante and see if we could put a motor in the glider and see if we can make it a little bit better. Okay, so in the early 1970s, one of my heroes comes onto the scene. It's a guy named Burt Rutan. That's him standing on top of Spaceship One, the first ever civilian spacecraft. Now, Burt is going to be a test engineer that is working on a little fighter jet, and then decides, hey, I'm going to get into designing and selling my own aircraft. And back in those days, you could order kit plans, like you can order kit planes today. Back in the day, you ordered plans, and Rutan would design these plans up, come up with the bill of materials and instructions on how to put it together, and then sell it in a magazine. And I think it was like $15 or something, which was like a lot of money, but it was like you're getting these high grade aircraft plans back in those days. And he builds the very Vegan first, and it's all wood, and then he starts experimenting with composites. And he noticed with the German sailplane world, they were able to get a lot of performance out of very little energy input, which allowed them to do all kinds of crazy things. I mean, just to get towed up and then just use the wind energy to keep the plane aloft was something fascinating to him. And so he thought, like, if we put a motor on this contraption, what could we do with it? And so that was his entry into the composite world, and then he created this aircraft, the Very the first ever all composite motorized airplane, which was originally a kit plane. You ordered the plans, you got the plans, and you went down to your local hardwood store, and the first thing that you had to do was build a hot wire machine to cut the foam pieces out that you're going to build the airplane out of. Now, there's a lot of challenges with building that airplane that way, simply because if you get the airplane off just a little bit, if it's not set just right, it'll never fly right, and you basically have to start over from scratch. But it was actually a pretty low-cost way to build a very high-performing aircraft. Now, later on, the Rocket League would go to use the Big Brother version of this airplane, the Long Easy, and simply because it's hyper efficient. The stats on a lot of Rutan's composite aircraft blow away even modern aircraft. The challenge it always faced was that it just looks so wacky and so different than anything else. And so if you're not kind of a rebel at heart type of person, you're gonna shy away from this wacky looking airplane. You look at a Cessna 172, well, that looks like what you think of an airplane is, and then you go get it and you fly. But the thing is that the Veries could do everything the 172 could do, but for far less energy. That means like lower fuel cost and longer distances and you name it. And so Burt was one of the first people to step out and really try the composites, the composite world out, and really demonstrate that it was something to embrace, something to explore. And so this is like into the 70s, into the 80s, and even into the early 90s before people really start to take it seriously and start looking at how can we employ composites on aircraft. Okay, on October 25th, 2007, the A380 was introduced to the world officially. And all through the A380, there were these composite structures that were put together. And this was meant to compete with the Boeing 777 and the 747-400 and subsequent models after that. And they knew in order to be able to get the airlines to buy onto an airplane like this, they would have to put more people on it. Well, the problem is people weigh stuff, and so they were looking for ways how can we reduce the weight of the airplane so that way we can replace that weight with people. And so they went around and said, like, where can we put composites that would otherwise have been really heavy metal? And so you'll see all of these call outs for CFRP, which is a type of composite material they were using at the time. Structures. So from the tail cone, the section, you have the horizontal tail plane, the vertical tail plane, wing ribs, pressure bulkheads, all these things which on a Boeing aircraft were metal, on the A380 they were going to be composite. And this is the first time we see in heavy commercial aviation composites being used extensively for aircraft structure. But it would only get more ridiculous from here. Not long after the A380 comes out, the Boeing 787 comes out. Now, the 787 is actually nearly all composite. There's still metal on it, and there'll probably be metal incorporated on all aircraft going forward. But but the 787's fuselage is actually made on site there in Charleston, South Carolina, in with the really big machines that just weave carbon fiber together. Here they are working on one of those carbon fiber fuselages that are built there in Charleston. You can go inside the factory and see that on the back end, that whole circular structure spins and will allow the fuselage to move around, so that way the machines can do the carbon fiber layup the way that it needs to be. Now, what that did for the 787 was allow them to run simply two engines instead of four, which means they cut the fuel consumption significantly. Then when you add in some of the Rolls-Royce high bypass turbofan engines, it got even better, which allowed airliners to have a greater profit margin and lower the fare prices to increase their market share. So it was a big hit when it came out, despite having a couple of hiccups. It's very forward thinking. This aircraft has no manual circuit breakers, are all like digital circuit breakers. It was the first one to use lithium-ion batteries, which got them in some trouble because they started catching on fire. But it's also the first time it's ever been employed. So it's a very advanced aircraft that had come out. But one of its biggest contributions is that it really brought carbon fiber out of kind of the hinterlands and the all. This is just a material that we use for something that's in the corner over here or some place that we don't really care about, to making it a legitimate part of the structure and working through all the challenges that come with carbon fiber. Like you can't have just regular carbon fiber fly around a storm, because if it gets struck by lightning, it'll explode. And so they had to figure out how to inlay lattice work in there to build a Faraday cage to help dispense with the lightning. So you have all those types of challenges that come with the new material, and the 87 really was the first one to step out and use composites the way that they should be. Okay, so since we've been using the 737 MAX as our kind of test subject to learn off of, this is where you can find composite structures in on the 737 MAX. Now, if you'll notice, it's a 737 NG frame, so there's still a lot of metal on it. Matter of fact, if you've been paying attention to the news as of the time that this has been recorded, Spirit Air and it is about to, or has gone bankrupt, and Boeing's gonna buy them out, or has bought them out, depending on when you watch this. And what Spirit does is they build the metal fuselages. And in all reality, Spirit's kind of behind the times, because all the fuselages are going towards carbon fiber anyways, just like this. But let's look at the max and kind of break down. The one thing I want you to take away is like notice that there's three different types of or composite materials on there. The first one is carbon fiber reinforced plastic. That's CFRP that we looked at on the A380. The other one is glass fiber reinforced plastic. Now that's fiberglass, like you would have a fiberglass boat, but it's been reinforced by plastic. Then you have glass fiber and carbon fiber reinforced plastic honeycomb sandwich. We're going to talk about what honeycomb is and sandwiching is here in just a little bit. But the main takeaway is that these structures are high strength, corrosion resistance. They increase fatigue life, so they can last a lot longer, and they're super lightweight. So notice even your flight controls in your tail, they're carbon fiber. Your engine fairings are carbon fiber. You have those canoes that the flap tracks go in on the bottom side of the wing. They're all carbon fiber and glass fiber mixed. The nose gear door up front, it's carbon fiber. As they kind of progress on, they're always thinking like, okay, well, what can we replace with carbon fiber instead of using metal? Simply because it saves so much weight and it saves so much money. Okay, so let's start off by just giving a general definition for what a composite is. So an advanced composite material is made of fibrous material embedded in a resin matrix, generally laminated with fibers oriented in alternating directions to give its material strength and stiffness. Now you can find these types of structures on fairings, flight controls, landing gear doors, leading and trailing edge of panels on the wing and stabilizers, interior components, floor beams, floorboards, vertical and horizontal stabilizers, primary wing fuselages, turbine engine fan blades, and propellers. The turbine engine fan blades are actually a new introduction of those that have kind of like become a big thing in commercial aviation. All right, so why are these things so special? All right, if the directions change the strength and stiffness, what's all that about? All right, so an isotropic material has uniform properties in all directions. So like metals like aluminum and titanium are examples of isotropic materials, meaning that if you take a piece of aluminum, it's not differentially stronger from side to side, backwards to forward. It's just a piece of metal, and that makes sense, right? If you pick up a steel plate and try to bend it, it doesn't really matter which direction you try to bend it from. You're not going to be able to do it because it's a steel plate. It's really, really strong, right? All right, now a composite material is only strong and stiff in the direction of the fibers. All right, so that means that like if you had like a unidirectional carbon fiber plate that we make, then you turn around and you can try to bend it one direction. You won't be able to do it, but you'll be able to bend it in the other direction because you're not going against the fibers there. You're not going against the grain of that plate. Now, composite material is only strong and stiff in the direction of the fibers and are said to be anisotropic, having mechanical or physical properties that vary with the direction relative to the natural reference axis inherent to the material. It's a big, long-winded way to say what I just told you. All right, so the structural characteristics properties such as stiffness, dimensional stability, and strength of the composite laminate depend on the stacking and the sequence of the piles. So any sort of fiberglass, carbon fiber structure, whatever else, is not just a piece. It's not just like a weave of fiber. It's going to have multiple fibers put on top, one on top of the other, and all running in different directions to create the strength that's needed for that particular piece. All right, now that means that fiber orientation is really, really important. The strength and stiffness of the composite buildup depends on the orientation and the sequence of the piles. The practical range and strength stiffness of carbon fiber extends from values as low as those provided by fiberglass to, get this, as high as those provided by titanium. So you could expend a lot of money on titanium and get the weight cost that comes with that, or you could use carbon fiber. And so a lot of times, carbon fiber is your better orientation. Now, this graphic here shows that the fibers in a bidirectional material run in two different directions. So bidirectional meaning it's going two different directions, right? And they're typically set up to be 90 degrees apart. They could be different depending on the use of that stuff, but this one in particular is 90 degrees apart. A plain weave fabric is an example of a bidirectional ply orientation. These ply orientations have strength in both directions, but not necessarily the same strength. strength. So that means that, like, if you look at the unidirectional, like if you were to pull on it or compress it or roll it or whatever else, you would encounter a certain level of resistance. But if you were to try to do it up and down laterally and roll it that way, then you would be able to do it pretty easily. You'd be able to make a tube out of it. All right. But the bidirectional, you might end up having some sort of resistance. But even though you have that resistance, it wouldn't be exactly the same based on the level of plies that are in that stack and the orientation of those plies. Now, the more realistic type of stack up that you're going to get with any sort of carbon fiber part is likely going to be a quasi-isotropic material layup, or what you're looking at right here. You're going to have a sequence where the layup is stacked at the 0 degree, negative 45, 45, and 90, and then it's going to repeat backwards, and then count down to negative 45, 45, 90, 0, and that's going to allow the carbon fiber to be stacked up so that way it has a pretty uniform strength I guess matrix for that part. But yeah, that's called a quasi-isotropic material layup. You'll probably never hear anybody actually say that unless you get into engineering or you go really deep into the carbon fiber world. But so what of it is that way. That is how a carbon fiber part functionally works. Is that you have these different fibers with different strengths in different directions, but you've rotated them around in the plies to allow a fairly uniform strength matrix from any one particular direction. Or you can stack it up so that way it's weaker in one direction but stronger in the other if you have to carry a particular type of load, which happens. You'll end up having parts. And that's why, like, some carbon fiber can't be used in one place that another sort of stack up could be used over here, is because the stress test of that airframe has rendered that we have to have a certain carbon fiber stack up and certain type of carbon fiber being used in a very particular way at a very, very particular place, and they can't necessarily be interchanged. And this is why. But yeah, so let's talk about the warp clock. Okay, a warp indicates the longitudinal fibers of a fabric. The warp is the high strength direction due to the straightness of the fibers. A warp clock is used to describe the direction of the fibers on a diagram, spec sheet, or manufacturer's sheet. If the warp clock is not available on the fabric, the orientation is defaulted to 0 as the fabric comes off the roll. Therefore, 90 degrees to 0 is the width of the fabric across. So if you look at your fibers that are running on this warp clock, if the fibers were, say, at the plus 45, you would have fibers running on that plus 45 orientation. If it was negative, it would be 90 degrees to the left of that, and it would be going the opposite. 90 degree fibers run the horizontal, and 0 degree fibers run at the vertical. Now, you'll notice that there are fibers that still have to give a lattice work for those 0 degree fibers to run on. But the key here is that the high strength direction. So meaning that, like, you could have horizontal fibers that run through that are weaker, and then vertical fibers that run through that are stronger, and so that would be a 0 degree fiber because that's the direction of the high strength. And you'll start to see at different carbon fiber plies, they take different weaves, and we're going to talk about weave here in a second. They take different weaves into account and different fiber runs in account, so that way you can manipulate the fiber to get exactly what you want out of it. So it's extremely customizable, and there's a lot of different suppliers that will produce a lot of different types of carbon fiber to meet whatever need that you may have. Now, you as an aircraft mechanic, your primary job is going to be just replacing carbon fiber parts or repairing ones. So the only thing that you really need to know is that what is the orientation and basically the part number for the carbon fiber plies that were used on this part, and then how do I stack them up, and you'll get that out of the structural repair manual, so that way you can create a plug that will go into it, but we'll get into repairs. Okay, so a little nomenclature. A single grouping of filament fiber ends, which will make up your eventual carbon fiber fiber ply is called a roving. They can have 20 end or 60 end glass rovings, and you'll see that on some of the tech data sheets of the different carbon fibers. That it'll say, hey, look, this is a 20 roving, 60 roving, so on and so forth, and that tells you how strong that individual ply of carbon fiber is going to be. If it's got a real heavy number of rovings, then you can identify that with like more and more strength, at least in a certain direction. So carbon fiber rovings are identified as a 3K, 6K, so 3,000, 6,000, 12,000 rovings, K meaning 1,000 filaments. So it means that like there's in a single roving you could have up to 12,000 single little bitty strands of carbon fiber. Most applications for roving products utilize mandrels for filament winding and then resin cure for final configuration. So there's a little bit of resin that's laced into those. All right, so let's talk about tape. All right, so just like with any other type of fabric or anything else that you're going to have to lay up, you're going to end up needing carbon fiber tape. Unidirectional pre-preg tapes have been the standard within the aerospace industry for a long time, and the fiber is typically impregnated with thermosetting resins, meaning that they have a cure time that like you have to use it by, or else it'll set up and be be hard as a rock. But it also means that you don't have to worry about any resins or on there because they're pre-preg, and we'll get into what pre-preg is here in just a little bit. So you'll simply set them down, pull the little sealant tape off of it, and it'll set up and be part of the structure at that point. So that's unidirectional carbon fiber tape. Okay, let's talk about a couple of different types of weave. We've already talked a little bit about unidirectional weave pattern that contain fibers that all run lengthwise in the direction of the cloth. That's the strong direction. Unidirectional weaves provide exceptional strength in the lengthwise, the warp direction, but virtually no strength in the widthwise, meaning you could roll up and make like a little, like a pipe out of it. Okay, so second from the right, or second from the left, that is the plane weave. Now, plane weave is probably the most common weave pattern. It consists of a one-to-one pattern. The fiber bundles run both lengthwise and widthwise and can generate strength in two different directions. The over and under path of the fiber bundles creates a stable weave pattern, but they can work against each other if depending on what the layup is. So it works really well for flat or nearly flat areas with limited contours. But if you have to drape it, it'll distort or wrinkle. So that's why you can mainly find these in like flat airframe ribs and bulkheads and airframe skims with like limited curvatures, so like tops of wings and things like that. You won't see it in a wing to body joint or something where there's a lot of contour. Now, another weave pattern that's fairly common is a twill. And we don't have twill on here. We have a lot of satin weaves, but twill looks very similar to plane, except for you have each warp strand will pass over or under more than one fill strand at a time. So you'll get a designation like 2x2 or 4x4, where the warp strands pass under two strands and then back over two fill strands, or four fill strands and then over under four. They're less stable than plane weaves. They're more apt to fall apart, but that lack of stability is really useful whenever you're having to form a three-dimensional or contoured part like a cowling, a wheel fairing, or a wingtip. Okay, another common weave is a multi-axial non-crimp or non-knitted or non-weaved type of carbon fiber. A multi-axial non-crimp or non-crimp fabric, or NCF, consists of multiple layers of unidirectional fabric stitched together in different orientations. Now, why would you want that? A lot of times, these are actually used to build parts out of. They work really well for building up thicknesses quickly and can be used to create thick plates, and with that, smaller two-dimensional composite parts can be machined. So, if you look at like an all-composite airplane, like your aileron hinge point right there would be made out of NCF. Or if you were to go and look at, say, a certain spacecraft with carbon fiber plates on the bottom of it to help with the reentry of that craft into the Earth's atmosphere, it's NCF to build up the plates, so that way you can then do other things to it to allow it to enter the atmosphere. So this is this is actually really useful, but you're not going to see it used probably like on the aircraft structure itself. It's going to be rather parts being milled out of it. Now, I keep saying carbon fiber as if it's the only composite material that's out there, and that's actually wrong of me. It's just kind of a force of habit. But there's actually several different types of materials that you can make composite structures out of. The first of which being fiberglass. That's the most common one that you'll see. This is what boats are generally made out of. You can find all kinds of parts probably on your car made out of fiberglass, and so glass fiber is very common. And it's commonly referred to as fiberglass rather. And it's most common because it's the most cost effective. It's the cheapest one out of all the different options that you have, and it has applications go back to the 1930s. Matter of fact, the first fiberglass boat was actually built by the Nazis. They took they built a fiberglass hull and then filled it full of which would effectively was expandifoam. And the thinking was that like it was so buoyant that if it got hit by a torpedo, the torpedo would just pass through it, and the boat could just keep on trucking along. And that actually happened a few times. And so the torpedo, because it didn't hit anything metal, didn't detonate. And so since it didn't detonate, then you didn't have to worry about any sort of explosion or anything else like that. Now the glass fiber is primarily composed of silica-based glass, which actually makes it hard to cut and hard to work with. But it's cheap, and so it still gets used a lot. It's about 5 to 25 microns in diameter, and then those all come together to make a roving, and then they get coated with a chemical finish that helps protect the fibers and promotes chemical adhesion with polymer resins. Now, there's two types. There's S-class and E-class. S-class is for strength, so that's going to be what your boat hull is going to be made out of. But E-class is going to be more for electrical application. So if you've ever cut into a piece of coax and they have those fibers running through it, that's going to be your E-class. But that's fiberglass. You'll actually use that. You'll see it still on aircraft because there's certain applications where it simply just does better, or maybe it's cheaper, or whatever the scenario is. It's actually still really useful, despite the fact that it doesn't perform as well in a lot of areas like carbon fiber or aramid or one of the other composites do. All right, so aramid. Aramid is best known for its name whenever it's employed in a bulletproof vest called Kevlar. If you've ever been in the military and you had to walk around with SAPI plates in and those little flexible plates right there, that's all aramid. Now, it's used for that because it can it can absorb a significant amount of energy and impact without breaking or tearing. It's abrasion and heat resistant, non-conductive, and has a low coefficient of thermal expansion. In about the 1970s, a company called DuPont came out with it, introduced it in, and the bulletproof vest really became a thing. Now, outside of that, it gets used in aviation pretty frequently in things like jet engine enclosures, radomes, luggage compartments, and helicopter rotors. However, even though it's extremely tough and hard to break, it does have a couple of drawbacks. Mainly, its susceptibility to UV degradation and moisture absorption. It's also it can be more difficult than carbon fiber and fiberglass to bond with the resin, so it's actually kind of difficult to work with. And then whenever you cut it, it'll leave like a fuzzy surface finish, so it doesn't cut clean like the other glasses do. And on top of that, since it's so tough, cutting tools get wore out by them. You end up having to sharpen your tools, replace blades on a pretty regular basis, so it becomes expensive just to manufacture and work with. Now, even though it has high impact resistance and low weight, it's actually not as strong as carbon fiber, but it costs about the same amount. So it kind of makes it you have to want to use aramid for exactly what it's good for, and not it's not like a replacement material at all. It's actually cheaper a lot of times or better a lot of times, just use carbon fiber rather than aramid. So yeah, that's aramid, Kevlar, Nomex, all the same material. Okay, the last one we're going to talk about is boron. Boron was actually kind of innovative because it was the first time carbon, or well, not carbon fiber, but first time a composite was used in a high performance structural aerospace application. So the F-14, and this is from Top Gun. It's like an artist rendering of Tom Cruise in that scene where he's running down the runway with the F-14 taking off. The F-14 stabilizer skins utilized boron fiber composites, while the boron fiber epoxy prepeg was using its horizontal stabs and the vertical stabilizers and rudders of the F-15 going into the 70s. So this is actually a pretty big step for carbon fiber. You think that like you have German sailplanes being used it, then all of a sudden you have this kind of crazy aerospace designer starting to use it, and at the same time that Rattan's coming online, they're all talking and they realize, hey, look, there's something to this, but we have some limitations that we have to deal with, and so they started experimenting with different types of fibers, and next thing you know, you get boron being employed on what was the Navy's premier fighter jet all through the late 70s and through the 80s, and that's pretty cool. Now, in modern times, the MQ-1B Predator UAV used this type of fiber composite on the upper spar caps of the wings, so that way you could actually increase its load. So if you've ever been around one of these things, they're really long. They have a really long tapered wings, but you look at it and you'll see Hellfire missiles stacked up on it. And you're always wondering, like, how in the world did they manage to get so much weight on there? And part of it is, at least in part, to boron fiber, because they actually replaced the upper spar caps with that boron fiber oriented the correct way. It could actually take a high compressible load, which means it keeps the wings from bowing up so bad. And you can see on the picture it's bowing up a little bit, but if it was done pretty much with any other type of fiber, it would really start to collapse it, and you would reduce the structural integrity of the aircraft, and you wouldn't be able to carry as much. And so it really is pretty innovative to have it on there. Anyways, how does boron work? What makes it so interesting? It has a larger fiber diameter than the other common fiber reinforcements at 76 microns to 142 microns. That's a pretty significant jump up, and that jump gives it a high compressive strength and low efficient thermal expansion. In fact, the James Webb Space Telescope actually used boron fiber interlaced with other carbon fibers, and it actually created a material that had no thermal expansion whatsoever. And that's a pretty big deal, because you think about, like, in space, you have like extreme grades of temperatures: super duper cold, super duper hot, and in between. Well, being able to have a material that has no expansion whatsoever, very 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 low expansion, and still super lightweight and super strong, really is some space age technology that we should celebrate, and we celebrate thanks to boron fiber. So those are your three types. The other kind of like honorable mentions would be polyethylene and Integra, that get used for very specific applications out in the industry. Unlikely to come across it. You'll definitely see fiberglass. We have fiberglass on our hangar floor right now. You'll definitely see carbon fiber, because we're going to teach you on carbon fiber, because that is kind of the material of the age, that you're going to see more and more carbon fiber aircraft coming out there. I mean, you just think, even in Arkansas, Game Bird 1 from Game Bird Composites, that's a carbon fiber aircraft. The Dark Arrow 1 from Dark Arrow is a all carbon fiber kit plane. Well, they're all carbon fiber. So you're starting to see more and more of this start to come online, and it's definitely going to be the case with heavy commercial jets as they go forward. But yeah, so you'll see carbon fiber, you'll see aramid, even though you may not know that's what you're looking at, or may not know the part that you're handling is aramid carbon fiber, because it's used in very specific places, but it's definitely out there. And then boron, we'll just have to see, because the likelihood is that it's going to get used in certain applications going forward. The question is that how expensive is it, and what are those applications of where they're going to employ it at. So you may not see it as prevalently, but that is the carbon fiber fibers. Now, when we're talking about composite layup, on commercial aircraft, I wanted to bring this to your attention. It doesn't really fit neatly in a category, but it's the metal foil that gets used inside of those layups. Now, this is a graphic that kind of shows you like from the paint to the primer to the fiberglass or the carbon fiber, a surfacer, and then it says metal foil, and then fiberglass, and then more composites underneath there. Now, what is the metal foil for? The metal foil basically builds a Faraday cage around the aircraft, so that way if it gets hit by lightning, it doesn't. It distributes the lightning evenly throughout the whole skin of the airplane and then out through the static wicks. If it didn't do that, what would happen is that all that lightning's power would be concentrated on one spot, and it would cause an explosion that would take the aircraft out. Now, lightning strikes happen pretty commonly, probably more commonly than what you may think. You very well may have been on a flight somewhere that got struck by lightning, whether or not you realized it or not, because it is pretty commonplace. Now, with that being the case, you can't fly carbon fiber aircraft, in and out of socked in airports, in Dallas, Atlanta, or something with a big storm system sitting on there. Because the moment that the first airplane gets struck by lightning, you'll have like a spectacular fireworks show and then a lot of dead people. And so Boeing figured this out, I believe. Building the 87, and they started thinking through and trying to figure out like how do we fix this problem. Well, the fix to the problem was this metal foil, and so like if you work on one of those aircraft, this metal foil will be something you have to contend with. Either installing things, you'll have to cut the fiber down to where this metal foil is at, and then make sure that the bond is correct. You might have to replace parts of it if you're doing a repair, or at least be cognizant of it being there. And so this is something that you should know, and it's something that you're not going to see outside of the heavy commercial world. Like you're not going to see like Gamebird or Dark Arrow or any other small aircraft company put metal lattice work in their planes, at least not now. But you will see it on Airbus, Boeing, and those types of manufacturers. Okay, when we talk about carbon fiber or we talk about composites, we always call it carbon fiber, and that's only really truly about half of the equation. So the fiber filament and reinforcement is only the part that can support the load under tension. But whenever it comes to compression, you think about like just a fiberglass sheet. You can compress it with your hands. Like it's no big deal. So under compression, you have to have some other material to just make it hold its shape and then stand up to compressive loads, and that is the matrix. So there's a broad range of matrix materials that exist in composites. You generally will have thermoplastics and then polymers. So let's talk about the thermoplastic resins first. So resin is just a generic term to use to designate a polymer. So you'll hear a lot of guys in this world will just simply say epoxy because that's what they're using, but just know that epoxy is a certain type, and we're going to get to that here in just a second. But resin is actually the professional term to use for what the matrix is. So you have two parts. You have the fiber, then you have the matrix or the resin that goes into it that builds the composite part that we're going to be working with. Now, the resin and its chemical composition and physical properties fundamentally affect the processing, fabrication, and ultimate properties of composite material. Now, thermosetting resins are the most diverse and widely used of all man-made materials. They're easily poured or formed into any shape and are compatible with most materials and can cure pretty quickly, either by heat or by catalyst, into a solid that doesn't go back. Thermosetting resins are also excellent adhesives and bonding agents, so we use them a lot. Okay, so polyester resins are relatively inexpensive, fast processing resins and are used for generally low-cost applications. So very common, you'll see, this is actually probably the most common resin that's out there. You use them on boats, on cars, anything that doesn't, have a super high degree of critical load that could, if it failed, it could be like a really bad day, like say like an airplane wing or something like that. But yeah, so know that's polyester resins. We mention it because it's very, very common. You probably not going to use it. There's situations where you may, but probably not. A type of resin that you will see out in the wide world of aviation is phenolic. This is a phenolic block. It's like a little fiberglass block that gets used all over the place. Those little phenolic blocks are very, very common in anywhere that's got electricity running through it because they're non-conductive. Any place that might have like a high wear or tear, you'll see phenolic blocks being used. So you can get used to seeing that. You probably aren't going to pour any of it unless you're building parts for something or another in a very specific manufacturing environment. Most of the phenolics you're going to end up just seeing like either around honeycomb or in little parts and pieces throughout just about any airplane. Even old airplanes have phenolic composite parts in them. And probably the most common resin that you may come across is epoxy. They're extremely useful and widely used in airspace due to their superior mechanical properties and resistance to the environment. They just don't break down very easily with different changes in the weather and so on so forth. Now they also don't have a whole lot of shrinkage. So you remember back to our fabric class, we talked about like the dope shrinking on the wing and causing the substructure to be misformed or broken or anything else like that. Epoxy, you just don't have that. It just doesn't shrink as much. Now, there's complications to using it because it's a two-part setup. So you have to like weigh and mix those two, and you have to mix them thoroughly. And once they're mixed, you're on a clock, and you have to use them, or else they'll start to set up inside of your mixing apparatus, whatever it is. They're also extremely susceptible to UV light. That's why you'll see a lot of carbon fiber aircraft whenever they've been unpainted. It looks really cool, and you would generally want to be like, oh man, just keep it looking just like that because it looks like something from the space age. But then they immediately paint it. And the reason being is that epoxy resin will break down with UV light, and you don't want that. And so you have to get them painted. Now, epoxies are typically the most expensive, but they're more stable and offer really long shelf life, which we'll talk to here just towards the end of this video. But yeah, so that's epoxy resin, very very common resin that you're probably going to use out there in the wide world. Okay, the last one we're going to talk about is vinyl ester. Vinyl ester is really big with Glass Air owners. So this is a Glass Air. It's a kit plane that has really high performance. It's kind of like it's one of the fancier kit planes that you can buy. It's kind of the Cadillac of kit planes that are out there. But on its parts, it uses vinyl ester as their matrix. Now, the reason why they do that is because it doesn't take nearly as much Part B to really get the resin to set up. However, it also shrinks a lot as it sets up. Now, a lot of this doesn't really matter to the guys that order like a Glass Air kit or anything because they're not the ones casting or setting the carbon fiber up. But it does matter for manufacturing purposes. So that's kind of like one of the reasons that epoxy really won out on the matrix race is that it just works better, from a manufacturing standpoint. Now, before we get off of matrices, what I want to do is talk a little bit about pre-preg. Now, pre-preg is kind of a hybrid between the two. You notice on this right here, they have the carbon fiber, but it's sandwiched between two blue sheets. Now, the reason why it's sandwiched is because inside of that carbon fiber is a perfectly infused matrix of some variety, and so say it's called it epoxy. So you have like epoxy that's in there. Once you peel the blue sheets off, it becomes tacky and it gets activated by the outside air and it's ready to set up. And so pre-preg is cool because you don't have to worry about mixing the epoxy and then infusing it and doing all that kind of stuff. It's already ready to go. It's not cool because it has a shorter shelf life. It'll set up. So you only really want to order it whenever you know you're going to use it because it's expensive and you don't want to just take it, order it, and then set it up. Like one day we'll get to it because you're going to come back to a big block of it and it won't be useful to you. But just know that prepreg is out there, and you can get a wide there's a wide selection of different prepreg material, resin, so on and so forth. No, there. I'll tell you this: most manufacturers don't use it because of the shelf life issue. They would rather just simply go through the hassle of infusing their own or doing like wet layups on their own, rather than try to like work to a production schedule that's dominated by when their material is going to go bad. Okay, lastly, let's talk about core materials. Typically, in a composite structure, you'll have a surface that's painted. You'll have several layers of plies, and you'll come down to a core. That core is going to be made up of either honeycomb, foam, or balsa wood. Typically, most commonly is you're going to see honeycomb. These honeycomb cores, whenever you get them, they can be made out of any number of things, from craft paper, thermoplastics, aluminum, steel, titanium, aramid paper, fiberglass, carbon, and ceramics are all different possibilities that you could get with honeycomb. You'll get them, and you'll be able to bend them and move them around almost like it's kind of like a really thick sheet of paper. And the idea is that that honeycomb structure, that we borrowed from the bees, will be able to withhold a lot of compressive load and a lot of tensional load. Now, you take that, you layer, your composite, well, your fiber of whichever variety you want to call it, carbon fiber. You take your carbon fiber on either end, and it creates a panel that's extremely strong and extremely hard. Once it sets up, it's really pretty durable, and you'll see these all throughout the airplane that are built just like this. I mean, my first experience with this was on the floors of a OH-58 helicopter. We would do a tap test to look for voids inside of those just about every service that I can remember, looking to see if we could find any voids in the floor whatsoever. And the reason they use it on helicopters, a helicopter has to pull its own weight. Like literally, it has to like generate enough lift to just go straight up. 100% has to lift itself. An airplane, it uses a lift and kind of like leverages Sir Isaac Newton to get itself off the ground. So it's not as nearly as much work. However, a helicopter, you have to lift a lot of weight. So any place they can get to reduce that weight, they'll do it, but they have to maintain that the structural integrity and the strength. And so these honeycomb cores, ours were made out of aluminum, help in that to that end. So expect to see these out there in the wide world. Okay, another one that's really common is foam. So foam cores get used on home builds and lighter aircraft to give strength and shape to wing tips, flight controls, fuselage sections, wings, wing ribs, you name it. I mean, like they get used all over the place. Foam is super cheap. It's not as good as honeycomb. It's not as strong as honeycomb, but it's strong enough to provide the strength that you need to produce a part. We'll also use foam blocks as molds whenever we're cutting out our fiberglass or our molds for our composite parts that we make. Now there's a couple of different types of foam. One is polystyrene. Those are aircraft grade styrofoam with a tightly closed cell structure. That's probably the most common one you'll see, but you'll also see phenolic, just like the resin that we were talking about earlier. Phenolic has a very good fire resistant properties and can be used in a very low density but relatively low mechanical load properties. So you'll see phenolic foam get used. Polyurethane is good for producing fuselage, wingtips, and other curved parts of small aircraft. Generally inexpensive. It's resistant to fuel, which is a big thing with composites. How does that matrix react to fuel? And there's a lot of like trade secrets that get thrown around on how to produce a composite structure that can handle fuel. They You can also use polypropylene as opposed to polystyrene. Used to make airfoil shapes, can be cut with a hot wire. So that was the thing like Long Easy, like a lot of the Rutan builds are using those hot wires. And then polyvinyl chloride or PVC, so just like PVC pipes. They're a closed cell medium to a high density foam with high compression strength, durability, excellent fire resistance. Another good way to go. And then lastly, Rochelle or polymethacylamide. oxide, a closed cell foam used for lightweight sandwich construction, excellent mechanical properties, high dimensional stability under heat, good solvent resistance, just all around good deal. We actually had Rochelle seats at one point. Now, yeah, those are your kind of foam options for core material. And lastly, we have balsa wood. And balsa is like no stranger to the aviation world. You probably built balsa wood planes as a kid, or when I was a kid, you could buy them at a like Easy Mart, and they'd sell these little balsa wood flyers. You get them, put them together, and throw them. But the end result is the same. What you're looking at there is a picture of a balsa core with carbon fiber laid on top of it. That's what your honeycomb would look like. That's what your foam would look like. Same idea. And just you're changing out the core material. You choose those core materials based on the load it's going to carry, where it's going to go, what it's expected to do, what your budget is, what your weight budget is. Does it need to be super light? Can you sacrifice a little bit of weight if you gain somewhere else? Those types of engineering decisions. One of the kind of like the weak chinks in the armor of composites is the material itself that we just went over. It has shelf life. It has to be stored properly. It has to be mixed and weighed appropriately. And if that's not done, then it will slowly break down over time. So let's talk about the shelf life and the carrying of those composite materials. Okay, so when we talk about shelf life on both mainly pre-preg and then any of your matrix materials, there's three things to consider. One is the temperature that it's stored at. Now keep in mind, there's, and we'll get to this later, whenever you're doing a setup, you can put things into an autoclave. You can increase the heat and it'll speed up the time that the composite matrix will set up. Well, that works the same whenever it's not mixed and just sitting on a shelf. Most of your matrix will have like a date that you have to use it by, because like if not, it'll turn into a big clear blob that's totally unusable. So always pay attention to the temperature that it's sitting in. If it is super duper hot, let's say you're in the Mojave Desert or whatever, you're going to want to make sure that wherever you're keeping your material, that it's air conditioned and it's kept at a good stable temperature. And the engineering data that comes with that material will tell you don't exceed a storage temperature of whatever, because as you exceed that storage temperature, you accelerate the time that it's going to set up, and it'll cure, and you won't be able to use it. So you want to make sure you keep that in mind. The next one is sunlight. So sunlight will have the same effect. If you leave your materials out sitting there, the sunlight itself will heat the can up. As the can heats up, you get back to the temperature principle, and it'll turn into a big block that you can't really do much with. And then lastly is time. Time is something that you always need to pay attention to with composites, with pre-preg especially, but like any of your matrix materials, because the longer it sits, the more likely that it'll be unusable whenever you go to use it. And so this is where, like, if you're in any sort of manufacturing environment, you want to pay attention to, like, okay, we took the order in, we plan to start working this, at this time. So here's like a bracket of time when we can order our matrix materials to get them to come in, so that way we don't have to worry about a lot of these factors. You can't. It's not like sheet metal where you can just bulk buy a lot and then keep it in the back and then use it as you go, and then whenever you get to a certain level, reorder some or anything else like that. So like, remember, like they all have a shelf life. Like you can't use stuff that has sat for a long period of time. You have to use it inside of a certain window, and that's different for every single thing. And I won't go over the details of every single one, because even if I said, oh well, you have to use this epoxy inside of like a calendar year or whatever it may be, it's gonna there's other types of epoxies in that same family. They're gonna have a faster cure time or a slower cure time based on the chemical makeup of it and then what it's supposed to be used for. So you really need to pay attention to what you have, what the engineering data says about it, and then also the environment that you're keeping it in. It should be like in a climate controlled closet with the lights off, and you should be good to go for however length of time that matrix material should be there. But with that is all for Intro to Composites.